Magnetism is all around us, even if we can't see it or even always feel the attractive and repulsive forces between objects. A fridge magnet, an example of a permanent magnet, has this characteristic because of the structure of the material it is made of. However, just because something isn't permanently magnetized doesn't mean it can't behave like a magnet. Moving electric charge makes magnetic fields, which is why the swirling motion of molten iron and nickel in the Earth's core creates a magnetic field. It's just that on the surface, we're so far away from where it is being generated, a distance equivalent to driving from the southwestern to northeasternmost points in the United States, that it isn't strong enough to attract or repel magnets we are used to playing with. However, we can detect it with a compass. Normally, electrons shown here in blue move around randomly, but complementary to the example with the Earth, moving or changing magnetic fields will create moving electric charge or current in conductors. It was this discovery that eventually led to the use of electricity that we have come to depend on today. This was first demonstrated in an experiment performed in 1831 by Michael Faraday, a British scientist who studied chemistry and physics. It led to the discovery of electromagnetic induction, which is known as Faraday's law. Now you will get to recreate Faraday's experiment to prove it for yourself. In order to do this, you will need the multimeter, leads or probes, alligator clips, an insulated cylinder, copper wire. Be careful with the wire, as the ends may be sharp or pointy. As you may have noticed, we've given you a couple different wires with different diameters and different lengths so that you can experiment similar to how Faraday did almost 200 years ago. We've also provided different size cylinders so that you can also test how the diameter of the coil may or may not change things. Finally, you'll need a magnet. We recommend starting with the bar magnet. Inside the physics kit, you have two magnets, a ceramic magnet and a neodymium bar magnet. While the ceramic magnet is 2 times stronger than the Earth's magnetic field at its core, it's still relatively weak. The bar magnet is at least 20 times stronger, as shown by its ability to pull a clamp. Be very careful to keep these away from electronics like computers and phones, and keep your fingers out of the way so you don't get pinched. To set this up, you will need to plug the leads into the multimeter, turn on the multimeter, and change the setting to measure 200 millivolts DC, or direct current. Observe that it reads 0 volts. Because we have made a closed circuit, or a complete loop connection, this indicates that there is no observable current in the system. And then attach the alligator clips to the ends, ensuring that they are secure. Take one of the copper wires and wrap it tightly around one of the cylinders. You may need tape to help hold it in place. Ensure there is enough at the end for the alligator clip to attach onto. Connect one alligator clip to each end of the copper wire. Now, using the bar magnet, move it inside of the wire coil and watch the voltage. The current is directly proportional to the voltage in a circuit. Another way to say this is that if current increases, then voltage should also increase. Also, if one decreases, then the other should as well by a similar amount. Because of this relationship, if we are able to cause or induce flow of electric charges by the moving magnetic field, then we should be able to see this as a related voltage. A more familiar analogy adapted from the Institute of Physics may help. Imagine that you are holding a rope in a game of tug-of-war. In this case, the movement of the rope through your hands will be the current. Your grip strength will be the resistance. The heat you feel from the rope sliding through your hands is the stored potential, or the voltage. And the speed at which the rope moves is the magnetic flux, or the amount of change in the magnetic field over a unit of time. Assuming that your grip strength remains the same throughout, and that it is loose enough for you to let the rope slip through, you will feel the most heat or energy when the rope is moving fast through your hands. Similarly, you won't feel any heat when it isn't being pulled. And this is exactly what Ohm's law tells us, that the current is directly proportional to the voltage in a circuit. Another way to say this is that if the current increases, then the voltage should also increase. There are lots of ways you can experiment with this and see what variables make the most difference. It is a good practice when exploring to change only one variable at a time to see what effect it has or not on its own. We do this a lot in research, especially when we are exploring something new. To start, you can change any of the following: the number of turns in the coil. Just remember that our multimeter can't detect very small changes on a voltage that is already really small, so changing it by only a few turns either way probably won't show a difference. If you're very careful and have a steady hand, you can adjust how fast you move the magnet in and out of the coil, or changing the flux. We have provided a couple different tube diameters as PVC pipe pieces and a straw. This will allow you to test the area of the loop or the coil. The insulated wire has a larger diameter than the bare wire, which means there is more surface to carry current. Of course, you are welcome to use the smaller magnet as well, but the multimeter may not be sensitive and/or fast enough to detect the changes. Using what you have learned, make a prediction or hypothesis for each experiment and note your observations. Comment below to tell us what you have learned and what combination you think works best and why. So Faraday's law tells us the magnitude of the voltage that we should expect to see, but what about the direction of the current flow? Remember that the current doesn't just result in voltage, it also produces its own magnetic field, and the direction of flow will determine whether or not it repels or attracts nearby magnets. The direction of induced current is described by Lenz's law, which we will demonstrate using an apparatus in our lab that we like to use when students visit. We have a coil of wire wrapped around a cylinder similar to what we had before, except this is able to be plugged into a wall outlet to supply current. We also have an aluminum disc, which by itself is non-magnetic, as is demonstrated by showing no interaction with a common household magnet. Once energized, the coil will make its own magnetic field. We can use the right-hand rule to see that if the current, I, is moving in the direction of our fingers, the magnetic field, B, will be in the direction of our thumb. If we set the aluminum disc around the coil, what do you predict will happen? Feel free to pause the video to think about it and write your hypothesis. Okay, here we go, powering on in 3, 2, 1. What do you think caused it to pop up and to resist the pressure when I push down on it? We already established that it isn't magnetic on its own. So what is happening? All magnets have two poles, often referred to as north and south. Like poles, or north-north, south-south, will repel, but the opposites, north-south, will attract, and this is clear from the field lines. Opposite pole field lines go in the same direction, so they are additive, or combine. Like pole field lines point in opposite directions, so they will often offset or repel. From what we learned from Faraday's law, we know that the magnetic field created by the coil can induce a current in the aluminum disc because it is a conductor just like copper. We can also use what we learned about the right-hand rule to predict the direction of the magnetic field of the coil. If the current in the disc was in the same direction as the coil, in this case counterclockwise, as shown in the drawings with the blue arrows, then the poles would be opposites, and the disc would be attracted to the coil. It would also make the resulting field even larger, and in theory, this trend would continue, which we know can't be the case because otherwise bad things happen. Because energy must be conserved, meaning that it cannot be created or destroyed, then the induced field in the aluminum disc must oppose the field from the coil. This is why the plate shoots into the air and resists pressure. When we started the demonstration, you can see that the aluminum disc was at room temperature, about 25 degrees Celsius. Although you couldn't see it in the initial demonstration, the plate is also heating up, becoming almost too hot to touch due to the resistance. Resistance, similar to the analogy of gripping a rope, is opposition to electric current. If the grip doesn't change, then as the rope moves faster, or in this case there is more current, heat will be generated. As you can see, after exposing the disc to the field created by the coil for only 2 minutes, the temperature has already increased to 50 degrees Celsius, or about 122 degrees Fahrenheit. By limiting the number of electrons that can move, Energy is conserved through alternative paths of heat and light. This isn't always bad. For example, the resistance in your toaster causes the wires to glow red and dissipate energy into heating the bread. And this is also the reason that older filament light bulbs produce light. But if we want to make really big magnetic fields, which are necessary for the research we do in our lab, or for MRI systems in hospitals, then we need lots of current. Resistance makes this difficult because if we heat things up too much, they could melt everything into a puddle, which isn't very helpful. Superconducting magnets, which can be 300,000 times stronger than the Earth's field, or more than 2,000 times stronger than a refrigerator magnet, have basically no resistance because they are made out of specially designed materials and are kept super cold at the temperature of liquid helium, only a few degrees warmer than absolute zero. Let's quickly test how resistance impacts the demonstration we just did. This time, my hand didn't block it from popping off of the stand. This allows us to see how high it actually went. From this snapshot, we can see that the disc popped about 6 to 10 inches above the stand. Keep this in mind because we are going to compare it to what we do next to see if we can make it go higher. As we mentioned before, decreasing the temperature can help lower resistance. So let's try this with our disc after it has been dunked in liquid nitrogen, which, as you may know, or will soon learn from our other video, is very cold. This worked better because atoms in the material are jiggling less, making it easier for electrons to flow around them. This results in more current, a bigger magnetic field, and a pop over 3 times as high. To try this at home, you could buy a copper or aluminum tube from your local hardware store and perform a similar version of this by observing what happens when you drop a magnet through the tube. First, I'll demonstrate allowing the magnet to free fall, being only subjected to gravity. Now we will do the same, except this time we'll drop it through the copper tube. The drop lasted longer because of Faraday and Lenz's laws, and now you can share this cool physics with family and friends. We encourage you to continue to play, experiment, and explore with the items in your kit. With some help, you could try to make a generator as shown here. Use what you have learned to make a temporary magnet to pick up paper clips, or test the voltage on batteries.